How are you going to get your constraint force if you're asked to get the magnitude of the constraint force? How are you going to get that, please? How to get the magnitude of the constraint force? So let's write down the constraint force first. What was that? What's the constraint force? Lambda. Yes. It's a holonomic constraint. I can write it as lambda nabla psi. So it's lambda partial psi partial x in the I direction, partial psi partial y in the j direction. Equivalently, these are, like we said, the ax and the ay, right? So the magnitude of the constraint force is simply lambda as a magnitude, the absolute value of lambda, times the square root of ax squared plus ay squared. Actually, this was 4x squared, 4y squared. So this is simply 2l. This guy is 2 lambda l. So get lambda, you're done. You have the magnitude of the constraint force. Okay. Any question? Please, if you have any question, do not let it pass. No shame. Of course, I'm not expecting that you're experts on holonomic and non-holonomic constraints. Of course. No single undergraduate student almost on the planet knows holonomic and non-holonomic constraints. That's perfectly fine if you don't know it. Do you have any questions? Okay, let's do another example with an inherently non-holonomic constraint. I mean, this was a holonomic constraint that we differentiated to write in this form. Let's do another example with a non-holonomic constraint. Anybody wants this board? Like I said, I mean, this is the most general form of Lagrangian equation. We're not generalize it further. We're just going to keep applying it more over and over again. Just one thing here. You have the difference between a holonomic and non-holonomic constraint, okay, in principle. Just bear with me for a minute, please. What do you think about this constraint? Maybe three. Is it a holonomic or non-holonomic?
Non-holonomic.
Anybody in favor to non-holonomic? Holonomic? So what's the difference? The difference is that it's not a trivial difference. It's not a trivial one. That is, if you simply see it on velocities, then it's surely non-holonomic. Not because you can always write the holonomic one on velocities, right? Just differentiate it like we did last time. So so what's the criterion then? The criterion is you need to try to integrate. And this is, by the way, this is a very common prelim question in the dynamics and control section. You're always given a constraint on velocities and you're asked, is it a holonomic or non-holonomic? And yes, unfortunately, most students, if they see it from the first time it's on velocities, they quickly say it's a non-holonomic constraint. You need to try to integrate. This is x dx by dt, right? Equals to negative 3y dy by dt. Which means x dx is equal to negative 3y dy. And indeed, I can integrate this one, right? To get x squared over 2 equals 3y squared over 2 in negative plus some constant. In other words, you have x squared plus 3y squared equals constant. This is a surface, right? So the criterion is you need, for the sake of solving the Lagrangian dynamics problem, I don't care. Why? Because I simply will work with this form anyway. I simply need the coefficients of the velocity, so that's fine. But to classify the constraint as holonomic or non-holonomic, okay, to do that, you need to try to integrate. If you are able to integrate it, then it is what?
Holonomic.
Holonomic constraint. Okay? And this leads to, or invoked us to stress further the difference between holonomic and non-holonomic. When you have a holonomic constraint, it means that your entire motion, I have 2 degrees of freedom, x and y. X and y, okay? So 2 degrees of freedom subject to a holonomic constraint. Holonomic constraint. If it's a holonomic constraint, means that you cannot go in the entire x and y domain. Your configuration space at the beginning was the entire R2, the entire plane. If it's a holonomic constraint, it means that you have a reduced space. Why? Because here is the relation that governs, that dictates that the motion will only be on that surface. So you have a surface in the plane, whether it's a circle or parabola or whatever. Your motion will be only on that surface. You cannot swap all the domain. This is quite dictating, right? You're just gonna live on a slice on your plane. Whereas if it's a non-holonomic constraint, yes, I know that I have a constraint, but yet, because it's non-holonomic, I'll be able to swap the entire thing. So actually it is related with the notion of controllability of dynamical system. Okay? Because controllability has to do, can you reach all the points or not? Okay, if I have a dynamical system and I want to control it using this control, can you go from here to all the points or you cannot? If you have a holonomic nature of your system, then the answer is simply no. You will have a reduced system. Your dynamics will be reduced. I can actually eliminate the x here and have only 1 degree of freedom y. Okay? Any question about that? Yes?
What if the coefficients are functions of both x and y? Here it was only
That's
x
fine.
and y.
You still can integrate, right? Oh, you mean both x and y?
Yes.
This is both x and y. So separation doesn't work then. But there might be other techniques. And this is a whole area of research. Actually, we in 276 geometric nonlinear control, we do this. We give you theorems, if and only if conditions, and very easy checks, so that if you have maybe 3-4 constraints, you can immediately tell whether they are holonomic or non-holonomic. Or in other words, we call it integrable. Can you integrate it or not? You're given a velocity constraint. Can you integrate it or not? Okay? There are some conditions using Lie algebra that tell you immediately. It's very easy, but we will not go through in this course. Probably whoever here sat in 276 last spring, you would know what I'm talking about. Any question here? Okay, let's do another example quickly. We have two masses, M2 and M1, and they are rigidly connected. But then this guy has a knife edge constraint, which is its velocity has to be along that line only. Okay? Basically, it has a wheel. Okay? So this is M1, M2, and this is in the plane. Now you may add gravity and play however you like. How many degrees of freedom do we have? Let's list them first. So what about this guy? How many degrees of freedom does it have? Maybe 2. Okay, x and y in the plane. Okay, then what about this guy? should in general have 2 degrees of freedom x and y. But what? There is one rigid connection, so this will eliminate immediately 1 degree of freedom, right? And then you have this constraint that seems to be non-holonomic constraint because it's on velocities, right? So let's maybe add here, I have x and y for this mass, and this is L, so I will add here is theta. I can do the following, I can do xy, x1, y1, x2, y2, okay, subject to how many constraints? So I can have x1, y1, x2, y2, these are 4 q's, 4 q's. Then I have to write subject to how many constraints? How many constraints?
Length of the rod and the non-holonomic x.
Yes. Delta x squared plus delta y squared is L squared, and the knife edge constraint, right? The non-holonomic knife edge constraint. So this is 4 q's subject to 1 holonomic and 1 non-holonomic, if you like to do that. Of course, if we're not asked about the force in the rod, I will not account for all these degrees of freedom. I will live only with x, y, and theta. Unfortunately, I will not be able to reduce it further because this is a non-holonomic constraint. Let's write down the relation for this non-holonomic constraint. Can you give it to me? First, what does it say? It says that the velocity of this mass is along that line, which means the component along the perpendicular is what? 0, right? Because at the end of the day, I need to write something equal 0. So the component along that line is 0. This mass has position x and y, so it has x dot and y dot velocities, right? And now it's easy to get the component along the blue line. What's that component? X dot times what? Sine theta minus y dot cosine theta, this is equal to 0. So 3 q's subject to 1 non-integrable or non-holonomic constraint. You cannot reduce it further, and you will have to continue the problem with extra. I know that I'm living with extra degrees of freedom because I cannot reduce it further. Okay? So at the end, I'm expecting how many equations in total?
4, 5, 4. 1, 2, 3, 4, 5.
4 equations, right? 3 from Lagrangians for the 3 q's and 1 constraint. 4 equations for how many unknowns?
4.
Yeah, x double dot, y double dot, theta double dot, and lambda, the Lagrange multiplier. Okay. Okay. Do you want me to do it, or you're fine? How many wants to do it? Okay, let's do it. So R1 of the first mass. This is the first mass, this is the second mass. So simply it's x in the I direction plus y in the j direction, right? R2 for the second mass. Yeah, I mean, I just said that I have it somewhere here, the inertial axis, but you guys are expert on that. R2, the second mass is whatever R1 here, x and y, but you have L cosine and sine. L sine theta in the I direction, and L cosine theta in the j direction, right? You simply need to differentiate once. Luckily, no more accelerations in this course.
Isn't it L cosine?
Cosine theta I.
Yes, you're right. Thank you. You're paying attention in the Halloween day. Very good. So R1 dot is x dot in the I direction, y dot in the j direction. R2 dot is x dot, negative L sine theta, theta dot, y dot, L cosine theta, theta dot. Okay? It's good that we do it because we need to do the kinetic energy carefully, please. I know that it's tempting that you do it very fast. Please don't lose just points for silly things like this. The kinetic energy, do it mass by mass. It's 1/2 m1 times r1 dot squared. R1 dot is a vector, so it has two components. The square of it is simply square of this guy plus square of that guy. So the square of this guy plus square of that guy. Plus, the second mass is a bit more complicated. So again, it's 1/2 m times r2 dot squared. Please bear with me for a minute here. In the first component square plus the second component square. Okay? So this is how we do it. It's not each term squared. Because you will have products now. So this will give you what? Let's see. Will give us, again, I will also assume that M1 is the same as M2 as M, just to make the problem simple. So this 1/2 m, x dot squared from here and there, y dot squared from here and there. And here we'll have L squared sine squared, L squared cosine squared, so this is L squared theta dot squared plus. The product term from here is
Minus 2x.
minus 2L, right? So 2L theta dot negative x dot sine, and here is y dot cosine. Okay? Any question about that? Any question about that? So this is just something squared, first squared, second squared, and the product. Okay? Any question, please? What do you think about this term in parentheses? Why 0? This is the constraint, exactly the constraint equation. Luckily, it's not always the case, but luckily, here you have it. Okay, so my kinetic energy expression actually is not that messy. What about your potential energy? Well, it's m1 gy and m2 gy plus L sine theta, which is 2 mgy plus mgl sine theta. So your magic quantity, the Lagrangian is T minus V, is 1/2 m